Yep, I am shit. I've been live. Yep. And so today we will continue where we were yesterday. Yesterday we were reading about the history of the Unix operating system, and today we will move forward. Yesterday we completed chapter one, number one, and today we will move ahead. And yep, it is somewhere here. Here you go. Yep, that is it. And a little smaller. And we were on chapter number two. Let's go there. We did chapter number one, and chapter number one was mostly about how Mr. Brian Kernighan, and this is just his book, which I'm just reading here on the stream. This is more of a audio book. It is just bad. I don't know why I'm even doing this stream, but I started it, so I have to finish it, right? At some point, I realized that I was 3 weeks from an operating system. That is Ken Thompson. The Unix operating system was born in 1969, but it didn't spring into existence out of nothing. It came out of the experiences of several people at Bell Labs who had worked on other operating systems and languages. This chapter tells that story. Yep, a bit of technical background. This section is a short primer on basic technical materials that forms the central topics of this book: computer, hardware, computers, hardware, software, operating systems, programming, and programming languages. If you are already familiar with these topics, skip ahead. If not, I hope this will bring you to speed enough that you can appreciate what it's all about. If you want more detailed explanations aimed at non-technical readers, you might like my Understanding the Digital World, though I am not unbiased. Okay, a computer is fundamentally not much more than a calculator, like the ones that used to be separate gadgets but are now just applications on your phones. Computers can do arithmetic computations exceedingly fast, however, billions per second today, though it was significantly less than million per second in 1970s. A typical computer of the 1960s and 1970s had a repertoire of a few dozen kinds of instructions that it could perform: arithmetic, add, subtract, multiply, divide, read information from primary memory, store information into primary memory, and communicate with the devices like disks and anything else that might be connected. Plus, one other crucial thing: the repertoire included instructions that decide which instructions to perform next, thus, what the computers will do next, based on the results of previous computations. That is what it has already done. In that way, a computer controls its own destiny. That is a good way to put it. Instructions and data are stored in the same primary memory. Instructions and data both are stored in the same primary memory, which is usually called RAM, for random access memory. If you load a different set of instructions into the RAM, the computer does dif- if you load a different set of instructions into the RAM, the computer does a different job when it executes them. That's what's happening when you click on an icon for a program like Word or the Chrome browser. It tells the operating system to load the instructions for that program into memory and start to run it. Programming is the process of creating the sequence of operations that perform some desired task using some programming language. It is possible to create the necessary instructions directly, but it is a difficult chore with many clerical details, even for tiny programs. So, most of the advances in programming have involved creating programming languages that are closer to the way that humans might express a computation. Programs called compilers, which of course have to be written themselves, translate from higher level languages closer to human language, ultimately to the individual instructions of a specific kind of computer. Yep. High-level languages were formed which helped humans to write more complicated pieces of code. Finally, an operating system is just a big and complicated program built from the same instructions as ordinary programs like Word or a browser. Its task is to control all the other programs that are trying to run and to manage interactions with the rest of the computer. Okay, this is pretty abstract, so here is a small concrete example of what programming is. Suppose we want to compute the area of a rectangle from its length and width. We might say in English the area of product of the length and width. Writing it on the board in school, a teacher could say that area is computed with this from formula. In a higher level language, we could write area equals length into width, which would be the exact form in most of the popular languages today. A compiler translates that into a still readable but machine specific source of machine instructions for a computer. That sequence might look like this for a simple hypothetical computer. Load length, multiply width, store area. That is, I don't know, that is a bit higher level language than the assembly language. Compiler translates this in still readable but machine-specific sequence of machine instructions of a computer. That sequence might look like this. Yep. Finally, a program called assembler converts that sequence of some or more less readable instructions into a sequence of machine instructions that can be loaded into the primary memory of a computer. When those instructions are executed, they will compute the area from the given length and width. Of course, this glosses over any number of details. How do we specify compiling and loading? How do the length of and width get into the computer? How is the area printed? And so on. But it's uh, but it's the essence of the story. If you prefer to see a working example, here is a complete program in the C programming languages that reads a length and width and prints the area. Okay, declared three floats, length, width, and area. Scanf scanned two floats. They are length and width. Area equals length into width. Print area in floating point. This program can be compiled and executed on any computer. Someone is familiar, Everyone is familiar at least with the names of modern operating systems like Windows and Mac OS. Cell phones run operating systems like Android and iOS. And I hope my screen stream is not stuck, and it is not stuck. That is cool. Now, yep. An operating system is a program that controls the computer, sharing the resources among programs that are running. It manages the primary memory, allocating it to run programs as they need it. On a desktop or laptop, the operating system lets you run a browser. On a desktop or a laptop, the operating system lets you run a browser, a word processor, a music player, and perhaps a little area computation program, all at the same time, switching its attention to each as necessary. It also controls the display, giving each program screen visibility when requested, and it manages the storage devices like disks so that when you save your Word document, it is preserved so that you can recover it and resume work later on. Operating systems are cool. The operating system also coordinates communication with the networks like the internet. So your browser can help you search, check in it, check in with friends, shop, and share cat videos all simultaneously. It's not so obvious to non-programmers, but an operating system also has to protect programs from other programs in case they have errors, and it has to protect itself from errant or malicious programs users. Something similar is going on with the operating systems on phones. Underneath, there is a lot of action to maintain communications via a mobile network or Wi-Fi. Phone apps are exactly the same area. Apps are exactly the same idea as programs like Word, though often different in detail, and they are written in the same programming languages. Operating systems today are big and complicated programs. Life was simpler in the 1960s, but relative to the time they were still big and complicated. Typically, a computer manufacturer like IBM or DEC Digital Equipment Corporation would provide one or more operating systems for its various kinds of hardware. There was commonality at all between hardware from different, no commonality at all between hardware from different manufacturers, and sometimes not even between hardware offerings from the same manufacturer, and thus there was also no commonality among operating systems. Okay, operating systems were different. CTSS, common time sharing system, compatible time sharing system. Multics, the first operating system. To further complicate matters, operating systems were written in assembly language, a human readable representation of machine instructions, but very detailed and specific to the instruction repertoire of a particular kind of hardware. Each kind of computer has its own assembly language, so the operating systems were big and complicated assembly language programs, each written in the specific language of its own hardware. This lack of commonality among systems and the use of incompatible low-level languages greatly hindered progress because it required multiple versions of programs. A program written for one operating system had to be in effect rewritten from scratch to move to a different operating system or architecture. As we shall see, Unix provided an operating system that was the same across all kinds of hardware, and evenly it was itself written in a high level language, not assembly language, so it could be moved from one kind of computer to another with comparatively less effort. CTSS and Multics. The most innovative operating system for the time was CTSS. The compatible time sharing system was an operating system, okay, which was created at MIT in 1964. Something happened in 1964. Well, CTSS was created. Most operating systems in that era were batch processing. Programmers put their programs on punch cards. This was a long time ago. Handed them to an operator and then waited for the results to be returned hours or even days later. Punch cards were made of stiff, high quality paper and could store up to 80 characters, typically a single line of program. So the six-line C program would have required six cards, and if a change was necessary, the cards would be have to be replaced. Figure 2.1 shows a standard 80 column card. Huh, punch card. That is much smaller than I thought it would be. Hmm. Fortran statement, Princeton University, and we are like the punches and stuff. Okay. By contrast, CDS's programmers used typewriter-like devices, terminals, like the Model 33 types in Figure 3.1 in the next chapter, that were connected directly or by phone lines to a single big computer, IBM 7094, with twice the usual 32K word of memory. The operating system divided its attention among the users who were logged in, switching rapidly from one active user to the next, giving each user the illusion that they had the whole computer at their disposal. This was called time sharing, and speaking from personal experience, it was incredibly more pleasant and productive than batch processing. Most of the time, it really did feel like there was no other users. There were no other users. Okay, Multics time sharing systems used to switch their attention from one programmer to the next and do their stuff. Okay, I can actually go into much more detail, but this is for the history of the thing. So I know that there was a operating system called CTSS, which was developed at MIT in 1964, which was a major improvement over the already existing batch punch card type computers. The CTSS was such a productive programming environment that researchers at MIT decided to create an even better version, one that could serve as an information utility to provide computing services to a large and dispersed user population. In 1965, they began to design a system called Multics, the multiplexed information and computing services. Computing services, mult is multiplex, mult is multiplexed information and computing services. Multics was going to be a big job since it involved ambitious new software and new hardware with more capabilities than the IBM 7094. So MIT enlisted two other organizations to help. General Electric, which at the time made computers, was to design and build a new computer with new hardware features to better support time sharing and multiple users. Bell Labs, which had a great deal of experience from creating its own systems since the early 1950s, was to collaborate on the operating system. Multics was intrinsically a challenging prospect, and it soon ran into problems. In retrospect, it was partly a victim of second system effect. After a success like second system effect, After a success like CTSS, it's tempting to try to create a new system that fixes all the remaining problems with the original while adding everybody's favorite new features. The result is often a system that's too complicated. It's the consequence of taking in on too many different things at the same time, and that was the case with Multics. The phase over-engineered appears in several descriptions, and Sam Morgan described it as an attempt to climb too many trees at once. Furthermore, one does not need to be much of a student of organization to anticipate that there might also be problems with a project involving two very different companies and a university in three locations spread across the country. Half a dozen or more Bell Labs researchers worked on Multics from 1966 through 1969, including Doug McElroy, Dennis Ritchie, Ken Thompson, and Peter Neumann, who had taken over Vic Wysocki's Wysots- Wysotsky, Wysotsky, Vic Wysocki's role when Vic moved to another Bell Labs location. Doug was deeply involved with PLI, public litigation, programming language I, the programming language that was to be used for writing Multics software. Dennis had worked on Multics documentation while a student at Harvard and with while a student at Harvard and worked on the device input and output systems at the labs. Ken focused on the input-output subsystem experience that proved valuable when he began work on UNIX. Though in a 2019 interview, he describes his Multics work as being a notch in a big wheel, and it was producing something that I did not want to use myself. From the Bell Labs perspective, 1968, it was clear that although Multics was a good computing environment for the handful of people that it supported, it was not going to achieve its goal of being an information utility that would provide computing services for the labs at any reasonable cost. It was just too expensive. Accordingly, Bell Labs dropped out of the project in April 1969, leaving MIT and General Electronics to solder on. Multics was eventually completed, or at least declared a success. It was supported and used until 2000, though not widely. Multics was the source of many real good ideas, but its most lasting contribution was entirely unanticipated. Its influence on a tiny operating system called Unix that was created in part as a reaction to the complexity of Multics. The origin of Unix 2.3. When Bell Labs pulled out of Multics, the people who had been working on it had to find something else to do. Ken Thompson 2.2 still wanted to work on. Yup, that is Ken Thompson. Uh, Ken Thompson, yep, still wanted to work on an operating system, but upper management at the labs had been burned by the Multics experience and had no interest in buying hardware for another operating system project. So Ken and others spent time exploring ideas and doing paper designs for various operating systems components, though with no concrete implementations. Okay. And then around this time, Ken found a little used DEC PDP-7 computer whose main purpose was an input device for creating electronic circuit diagrams. The PDP-7 was first shipped in 1964 and computers were evolving quickly. So by 1969, it was dated. The machine itself wasn't very powerful with only 8K 18-bit word of memory, 16K bytes. But it had a nice graphics display, so Ken wrote a version of space-time game to run on it. A player could wander through the solar system and land on different planets. It was mightily addictive, and I spent hours playing with it. The PDP-7 had another interesting peripheral, a very tall disk drive. Let me see. PDP-7 computer. So that looks like what the heck is that? It looks like something you would be using in World War to send and receive information. PDP-7. Okay. Yep. The stream got stuck somehow. I don't know why the fuck that happens. Mac OS screen. Yep. Oh, no, I messed up. I messed up. Transform, reset transform. Yep. And transform fit to screen. And this. Yep. I am visible. Yep, I am visible. And let's go. The PDB-7 had another interesting peripheral, a very tall disk drive with a single vertical. Later, credible folklore held that it was potentially dangerous to stand. This book is something that I should be reading on my own and not here on the stream because this seems like a fun read and not something to read on this. Maybe to something to read on the stream, but this is more theory, and I do not want to do theory. I'm much better at doing programming on the stream. Like I have only done 40 streams, so that doesn't matter. But at this point, I'm reading this to just complete this book and on the stream because I started this book on the stream. So I would like to complete this book on the stream. Yep, complete it on the stream. And I have Dennis Ritchie and Ken Thompson looking at me in the eye, and that is scaring me. Credible folklore that held that it was potentially dangerous to stand in front of it in case something broke, and the disk was too fast for the computer. And this presented an interesting problem, and can wrote a disk scheduling algorithm that would try to maximize throughput on any disk, but particularly this one. Now the question was how to test the algorithm that required loading the disk with data, and Ken decided that he needed a program to put data on it in quantity. At some point, I realized that I was 3 weeks from an operating system. He added to he needed to write three programs and one per week an editor, so he could create code, an assembler to turn the code into machine language that could run on PDP-7, and a kernel overlay, call it an operating system. Right at that time, Ken's wife went on a 3 week vacation to take their 1 year old son to visit Ken's parents in California, and Ken had 3 weeks to work undisturbed. As he said during a 2019 interview, 1 week, and we had Unix. By any measure, this is real software productivity. A couple of years after Ken and I both retired from Bell Labs, I asked him about the story that he had written the first version of Unix in 3 weeks. Here, verbatim, is his email response, which is completely consistent with the much more recent interview. Unix was a file system implementation to test throughput and the like. Once implemented, it was hard to get data to load it up. I could put read write calls in loops, but anything more sophisticated was near impossible. That was the state when Bonnie went to visit my parents in San Diego. I was dedicated that it was close to a time sharing system, just lacking an exec call, a shell, and an editor and an assembly, no compilers. The exec call was trivial, and the other three were done in 1 week each, exactly Bonnie's stay. What were the other three? Time sharing system, just an exec call was easy, shell, editor, and assembler. The machine was 8K, 18 bytes. 4K was kernel, and 4K was soft memory. Ken. The first version of a recognizable Unix system was running in mid to late 1969, so it seemed reasonable to say that that's when Unix was born. The early system had a small group of users, Ken and Dennis, of course, plus Doug McElroy, Bob Morris, Joe Osana, and through a bit of blind luck, me. Each user had a numeric user ID. Some of these IDs corresponded to system functions, not to human users. The root or super user was ID 0, and there were a couple of other special cases. IDs for real users started around 4. I think that Dennis was 5, Ken was 6, and mine was 9. There must be some cache in having a single digit user ID on the original Unix system. That, yep. What's in a name? Sometime during these early days, the new PDP-7 operating system acquired a name, though the details are murky. I have a memory of standing in my office doorway talking with a group that probably included at least Ken, Dennis, and Peter Neumann. The system had no name at that point, and if memory serves, I suggested, based on Latin roots, that Multics provided many of everything, and the new system had at most one of anything. It could be called UNIX, UNICS, a play on uni in the place of multi. An alternative memory is that Peter Neumann came up with the name Unix for uni, Uniplex Information and Computing Service. As Peter recalls, I remember vividly that Ken came in one morning for lunch and said that overnight he had written a thousand line one user OS kernel for the PDP-7 that Matthew had lent him. I suggested that he could make it a multi-user system and use enough. The next day he came in, and sure enough, the next day he came in for lunch having written another thousand lines with a multi-user kernel. It was the one user kernel that prompted the castrated multics concept of Unix. Peter had graciously said that he doesn't recall further specifics and so on. Deservingly nor or not, I have gotten credit for coining the name. Either way, Unix somehow muted it to Unix, which was clearly a much better idea. It was rumored that A&T lawyers didn't like Unix because of its similarity to Unix. Dennis Ritchie subsequently characterized the name as somewhat treacherous pun on Multics, which indeed it is. Biography. Ken Thompson. In 2019, in May 2019, Ken and I had a informal fireside chat at the Vintage Computer Festival East in Wall, New Jersey. My role was to ask a few leading questions, then sit back and listen. Some of the material here is paraphrased from that interview, which can be found on YouTube and which I have watched. Not completely, the starting, and I have it in my watch list. Ken was born in 1943. That is pretty fucking old. That is like El Pacino old. El Pacino was also born in. When was El Pacino born? Born. What the fuck? Wait, no. Bobby Fischer was born in 1944. El Pacino, yeah, I guess he was born in. Um, El Pacino was born in 1940, 1942. I would go with 1942 or 41. 42 or 41, 42, 40, fucking hell. 1940, okay. He was born in 1940, and Robert De Niro in 42, I would say then. De Niro, 1942, 1942, 1940, fucking 3. The same, nope, not the same year. Yes, the same year as Ken Thompson and Bobby Fischer. I know for sure 1944. 1944. 1943, okay. Fuck. Mikhail Tal, 1937. Mikhail Tal, 1937. It has. Okay, now it makes more sense. Yeah, Mikhail Tal and Bobby Fischer had age difference of 7 years, so I thought Mikhail Tal in 37 and then Bobby Fischer in 34, in 44. But no, shit, my bad. So Ken Thompson was born in 1943. His father was in the US Navy. So Ken spent significant parts of his childhood living in different parts of the world, including California, Louisiana, and a few years in Naples. California, Louisiana are these states? California, I guess, yep, is a US state. Okay, on the far west of the US. Okay, California. And Louisiana is also a US state. Yep. Louisiana into the south. Okay, California, Louisiana, and Naples, city in Italy or in Florida. Mm-hmm. Naples, city in Italy. There it is, Naples in Italy. It is also a city in Florida, and Florida is a U.S. state. Naples is a not even a city, a small fucking town in Florida, and Florida is there. Wait, Tampa, Tame Impala, Dallas, U.S., Salt Lake City, Seattle, or oh, those are I guess city capitals. Santa Cruz. Yep. The main cities are here because that is where the British first started to land. I guess the Vasco da Gama landed in Bahamas on this island. Nassau, shit, the main land is here, the capital is here. That is just crazy. Shit, my mouse stopped working. Yeah, one more thing. This is where Roanoke was, right? The lost city of Roanoke. Or was it here? No, I don't know. No, no idea. I guess it was probably here in the Caribbean somewhere, or here in the Upper Caribbean. Right. He was born in 1943. His father was in military, and he grew up interested in electronics and went to the University of California at Berkeley to study electrical engineering. He said that he found the electronics part really easy because it had been his hobby for 10 years before college. At Berkeley, he discovered the field of computing. I consumed computers, I loved them. At that time, there was no computer science curriculum at Berkeley. I was being invented. It was being invented. I was drifting along the summer after I graduated. Graduation was a surprise because I didn't know that I had gotten all the requirements. I was just going to stay in the university because I owned it. My fingers were in absolute everything. The main monster computer at the university shut down at midnight, and I would come in with my key and I would open it up, and it would be my personal computer until 8 a.m. That is just crazy. I was happy, no ambition. I was a workaholic, but no goal, but for no goal. In his final year in college, Ken audited a course taught by Elvin Berkeley, a Berkeley professor who soon afterwards went to Bell Labs. In the summer after graduating, Ken didn't apply for grad school because he didn't think he was good enough. Towards the end of the summer, Burley Burley Camp said, "Here is your classes. Here is your classes for grad school." He had applied for me, and I got accepted. When Ken finished his MS at Berkeley in 1966, Bell Labs was among several companies that tried to recruit him, but he explicitly said that he didn't want to work for a company. The recruiter kept trying. As Ken says, I skipped maybe 6 or 8 requirement attempts by Bell Labs again and no ambition. The Bell Labs recruiter came and knocked on my door at home. I invited him in. His story is that I offered him ginger snap and beer. This must be part of some odd California diet. Finally, Ken agreed to come to New Jersey at Bell Lab's expense, but only for a day and primarily to visit his friends from high school days. But when he arrived at Bell Labs, he was impressed by the names he saw. Very first thing I did was walk down the corridor of computer science research, and every name on the door on the way down, I knew it was just shocking. I was interviewed by two amazing people. When was One was Shen Lin, who was working on the traveling salesman problem. Shen Lin. I got my rent a car after the day and somehow they tracked me and there was an offer waiting at the third stop down the east coast. I picked up the offer and drove it from one stop to another, which was maybe 2 hours. Thinking about it, and when I got to the next friend's house I called them and said, okay. Ken arrived at Bell Labs in 1966 and started work on Multics, then on Unix as described earlier, so I won't repeat that here. Ken had a long-standing interest in games and was a chess enthusiast, as again he didn't like to lose, but at the same time, when he won, he felt bad for his opponents. So eventually he became a spectator only. In 1971, he wrote a chess playing program for PDP-11. This was promising enough that he began to build special purpose hardware to speed up computation. He started to build special purpose hardware. That is crazy. Example, to generate legal moves from a given position. Eventually, this culminated in Belly. Figure this. The chess playing computer that he and Joe Condon evolved from 1976 to through 1980. A chess playing computer. Okay. Belly figure 2.4 had a successful career. It was the first computer to become a chess master, a rating of 2200 in regular tournament play against human opponents, and it won the 1980 World Computer Chess Championship and several ACM ACM computer chess tournaments before retiring to the Smithsonian Smithsonian Institution. Dennis Ritchie wrote a short article for the International Computer Chess Association on Ken Thompson's activities with various games. Here on this page, it shows Ken's breadth of game interests, well, just beyond chess. There is also a description of Belly's winning win over Blitz 6.5 at ACM Computer Championship on December 5, 1978, with the comments from Monty Newborn, a computer chess pioneer and international master, David Levy, father of Levi Rosman, and these are the moves. Belly, okay, Belly chess computer, courtesy of Computer History Museum. Like this book is a courtesy of Mr. Ken Thompson. Chess games end with win, loss, or draw. The 50 move rule says that a player can claim a draw if there have been 50 moves without a capture or a pawn move. This prevents one player from just playing on when there is no way to force a win. Ken decided Ken decided to explore the question of whether 50 moves is the right number. He used Belly and some sophisticated database organization to evaluate all 4 and 5 piece games and discovered that some were winnable in more than 50 moves given optimal play. By this time, Ken was well known in the chess world, and sometimes grandmasters would show up at the labs to try their hand against Belly, particularly for endgames. I met world champions Anatoly Karpov and Visyanand just by being around on the right time, on the right weekends. Shit, Anatoly Karpov, Visyanand. Ken was also an avid pilot and regularly flew himself and guests around New Jersey, starting from the airport in Morristown. He got other members. Shit, he was. pilot, that is a crazy man. Of 1127 interested in flying as well, and at peak there were half a dozen private pilots in the 1127 Air Force. This group used to set off to view fall foliage or fly to some interesting place for lunch. Doug McElroy recalls, besides fall foliage in New England, fall foliage, what the heck is that? Huh. Change of tree leaves. Okay. Beside fall foliage in New England, the Air Force attended an eclipse in the Adirondacks thanks to Ken's piloting and Rob Pike's telescopes. Yeah. There was also a flight to observe a transit of Mercury. The astronomical theme in the UNIX crew began with Joe Osana's Hazel, which had controlled the Telstar ground station and to tell us and we used to tell us whether to find artificial satellites. Came next Bob Morris's Sky program, then Ken's essential event predictor Lee McMahon's star map made with my map program, and finally Rob's star catalog. In December 1992, Ken and Fred Graham went to Moscow to fly a MiG-25, courtesy of CatV.org. Ken Thompson preparing to take off. Set up from the normal Cassness figure 2.5 and 2.6 show Ken ready to go and taxing back after a flight. So it is Ken Thompson flying this thing. That is crazy. Ken and I retired from Bell Labs at the end of 2000. I went to Princeton and he joined Entrisphere, a startup funded by Bell Labs colleagues. In 2006, he moved to Google, where with Rob Pike and Robert Zrai Simmer, he created the Go programming language. I heard about his move from Entersphere, Entrysphere to Google from someone else. So I asked for confirmation. His reply, it's true, I didn't change the median age. I didn't change the median age of Google much, but I think I really got the average, really shot the average. Huh. I didn't change the median age of Google, but I really changed the average. Okay, first edition, 1971. This manual gives complete descriptions of all the publicly available features of Unix. It provides neither a general overview, see the Unix time sharing system for that, nor details of the implementation of the system, which remained to be disclosed. First edition Unix Programmer Manual, 1971. Bugs. RM probably should ask whether a read-only file is ready to be removed. A read-only file is ready to be removed. Section of manual pages for RM. Okay. Now PDB 7, and my stream is not stuck. Video is working, screen is working. That is cool. Yep, I can move forward with chapter number 3, the first edition of Unix, and this is more like reading an audiobook than learning. But at this point, I have to do this thing. The PDP-7 Unix system was interesting enough that people were starting to use it, even though it ran on a tiny computer and it didn't have a lot of software. Still, it was clearly useful and had become the preferred computing environment for a small group who found it more fun and productive than the big central computer. Thus, Ken Thompson, Dennis Ritchie, and others began to lobby for a large computer that would support more users and enable more interesting research. One of the early proposals was for the purchase of DEC PDB-10, which was popular at the universities and other research labs. The PDP-10 was loosely similar to IBM 7090 with 36-bit word like the 7090 and GE 635 and 645. What the fuck does that all even mean? And it had a great deal more horsepower than the wimpy little PDP-7. But it would also cost much more. The pers the proposal was for $500,000. The Multics experience was an all too recent bad memory, so the PDP-10 proposal never got off the ground. As Ken said, the management position position was we don't do operating systems, though perhaps it was more like we are not going to give you a lot of money for a big machine. I suppose that it could be argued that one positive role of management is to be cautious most of the time. So the people who want resources are forced to hone their proposals and focus their pitches. If resources are tight, that's more likely to lead to good, well thought out work than if there are no constraints. In any case, the Unix group came up with another idea to acquire a new mini computer that DEC had just announced, the PDP-11, which would cost more like 65,000 than 500,000 in 1971 dollars. This was rejected too, a remark from Sam Morgan in Mike Mahogany's 1989 oral history oral history interview explains some of the reasoning. The management principles here are that you hire bright people and you introduce them to the environment and you give them general directions as to what sort of thing is wanted and you give them lots of freedom. Doesn't mean that you always necessarily give them all the money that they want. And then you exercise exclusive enthusiasm over what they do. And if you mistakenly discourage or fail to respond to something later on, turns out to be good, if it really is a good, strong idea, it will come back. That makes sense. In hindsight, being forceful to work within constraints was a good thing, as Ken himself said in his 1983 Turing Award lecture. Fucking hell. Unix swept into popularity industry-wide change with an industry-wide change from central mainframes to autonomous minis. I suspect that Daniel Borrow, Bobrow would be here instead of me if he could not afford a PDP-10 and had to settle for a PDP-11. Daniel Barbaro, primary author of 10X operating system, which was written for the PDP in 1969. PDP and Unix for patent applications. Direct appeals for a machine field, but there was an alternative. Direct appeal for a machine field, but Bell Labs as a large and productive scientific research operation generated a lot of patent applications. At that time, it was being granted an average of almost one patent per day. Okay, that is cool. Patent applications were text documentations, but with some rigid format requirements like line numbered pages. No existing computer system could handle these oddities, so the patent department was planning to buy hardware from a company which promised software that would eventually produce applications in the proper format, though it could not do number lines at the same time. Joe Usana came up with another plan. The patent department would use a PDP-11 for operating patent applications. The Unix group would write the necessary software for them, complete with a formatting program that would print applications in the proper format and No, no one would be working on operating systems. Okay, this combination of ideas, slalom. This combination of ideas is slalomed around any residual management objections. Money for a PDP-11 came from Max Matthews, the director of the Speech and Acoustics Research Center. Max was supported because one of his department heads, Lee McMahon, was very interested in text processing, and all along with Usana was a promoter of the plan. The deal was approved. A PDP-11 was purchased, and Ken and Dennis quickly converted the PDP-7 version of Unix to run on it. The PDP-11 was a limited machine with only 24K bytes of primary memory and half a megabyte disk. The implementation used 16 bytes of operating system and 16 kilobytes for the operating system and the remaining 8K for user programs. Fucking hell, this shit too cute. 16 kilobytes for the whole operating system. Joe Osana wrote a program called NROF, New ROF, NROF, analogous to the existing ROF text formatter that was able to print patent applications in the required format. By the last half of 1971, yes, 1971, no war. Well, there were wars. Shit, it was no 1979 when Saddam Hussein became the leader of Iraq. 1979, Iraq and Iran wars. Well, last half of 1971, typists were cracking out patent applications on Unix full time. Chapter 5 has much more to say about text formatting since it was a major part of Unix's story in 1970s. That was during the day. At night, Ken Dennis and others were developing software on the same PDP-11. Development had to be done at night so as to not interfere with the typists, and it had to be careful. The PDP-11 had no hardware protection mechanisms to keep programs from interfering with each other's or with the operating system. So a careless mistake could easily crash the system, and an error in the file could lose everyone's work. But the experience was so successful that the patent department bought another PDP-11 for the Unix group, and that made it possible to do development full time. This version became the first edition of Unix. Figure 3.1. This is Unix. Well, this is Ken seated. This is Ken Thompson and Dennis Ritchie at PDP-11, 1972. Okay. This is a 1972 public relations picture of Ken Thompson and Dennis Ritchie using a PDP-11 running an early version of Unix. The computer itself is apparently a specific model called PDP-1120. The smallish round object at about head level are DEC tapes. These these are called DEC tapes, which were magnetic tape devices that held 144K 18-bit words. That is quite a bit for their generation, I suppose. Individual blocks could be read and written, so they could serve as temporary, slow but reliable disks. The tapes themselves were removable, so they were used for backup as well. Ken is typing at a Model 33 teletype, a sturdy but slow and noisy device. Basically, a computer controlled electromagnetic typewriter that could only print in uppercase at 10 characters per second. 10 characters per second. Huh? The Model 33 dates from 1963, but earlier versions had been in widespread use since the early 1930s. Teletype Corporation Corporation was a part of AT&T, and teletypes were widely used throughout the Bell system and elsewhere for sending messages and later for connecting to computers. Whatever was typed on the teletype keyboard was sent to the computer and responses were printed. Teletype Corporation was a part of AT&T, and teletypes were widely used throughout the Bell system and everywhere elsewhere for sending messages and later for connecting to computers. Whatever was typed on teletype keyboard was sent to the computer, and responses were printed in uppercase on a long roll of paper. The tops of the paper rolls are just visible in the picture. These are just visible on the picture. Arguably, one reason why many command names on Unix are short is that it took considerable physical force to type on a Model 33 and printing was slow. Someone even built an experiment portable Model 33. The keyboard and printer were shoehorned into a suitcase-like container that in theory could be carried around through a 55-pound 25 kg. You wouldn't carry it far. It had no wheels either. It was connected to a remote computer through a digital dial-up phone connection and a built-in acoustic coupler. Plug a telephone handset into a couple of rubber sockets, and the coupler converted data into sound and back again, rather like a fax machine. I managed to haul one of these terminals home a couple of times, but calling it portable was too charitable. Yup. Bob Morris. I've heard Morris. Morris Mano. Things improved remarkably. Yep, I am visible and stuff is working fine. Seems, and why is FPS going up and down? That is crazy. And reading this book like that is not very happy. Let me make this a little less so that my stream doesn't suck. Yeah. AT&T. Oh shit. Now things improved remarkably. Markedly when the Model 37 teletype came along. It had lower case letters as well as uppercase and was somewhat faster, 15 characters per second rather than 10. Though it was still strenuous to type on it. It had an extended type box so it could print mathematical symbols, which was useful for the patent applications as well as our own technical papers, and it could roll the paper back and forth in half-line steps, which made mathematical subscript and superscripts possible. And at this point, I am just barely reading this. Feeding paper into it was also a challenge. It took real contortions to load a new box of fan fold paper. Bob Morris once sent Joe Osana a mail message that consisted of 100 reverse line feeds. When Joe tried to read the message, the Model 37 sucked the paper back out and deposited it on the floor. Bob occupied the office across from me for a number of the early years. Robert Morris was a common name at Bell Labs. Indeed, there was a visitor named Robert Morris in the same office a few years later. So Bob frequently got misdirected mails, which he would dutifully sit back, explaining that he was the wrong Morris. One piece of mail kept on coming, an elaborate blueprint for some other part of the company that said, please initial and return. All attempts to head it off failed. So finally one day, Bob did initial it and sent it back. It never appeared again. The Unix room. Although each research MTS had a private office, much Unix development went on in a shared place called the Unix room. It was called the Unix room. Okay, it actually its actual location changed a couple of times over the years, but it was always a place to hang out, learn what was going on, contribute ideas, and just socialize. The original Unix room was uh, briefly on the fourth floor of building two. Okay, building two only had five office floors. The sixth floor was basically a service corridor, dingy, dimly lit, and lined with storage areas, holding dusty, abandoned equipment in locked wire cages. At one end, there was an open area with vending machines that offered appealing appealing coffee and almost inedible, appalling coffee and almost inedible pastries that fueled late night programming. And there were a handful of enclosed spaces, one of which was the Unix room for at least a decade. It held the PDP-11, the picture of Ken Thompson and Dennis Ritchie. Figure 3.1 was taken there. A few tables and chairs and some other terminal made it a good shared working area. One of the early non 1127 Unix enthusiasts, plural enthusiasts, was a very distinguished the theoretical physicist, now deceased, who I will call M space L. M space L, Unix room, espresso machine, and coffee grinders. Oh, that is cool. Eager to use Unix, he was forward thinking and in his use of computers in physics, and he was kind and generous person, but he would talk your ears off. Once he got started, there was no way to stop him, and you were in for an hour of one-way conversation. So someone scattered a small hole in the froster of the door to the Unix room so we could peer in before entering to see if he was there. It was called the L hole. At some point, the Unix room migrated to room 2C501 on the fifth floor at stair 9, just around the corner from my office. It also acquired a variety of coffee machines. Originally, the usual uh, carafes with a heater that kept the coffee warm until it burned. So the carafe did something that happened regularly, and then a sequence of ever more expensive coffee grinders and espresso machines. The last of which costed like $3,000 if my sources are right. Unix room denizens paid for the machine by passing the hat, and management paid for the coffee. The Unix room was just plain fun. There was always something going on. Some people worked there almost exclusively and rarely used their offices. Others would drop in multiple times a day for coffee and conversation. It's hard to overstate how important the Unix room was for pairing up with what colleagues were doing and for creating and maintaining a sense of community. In retrospect, I think that Bell Labs did a good job with the space. Private offices, though they cost more than open areas, give people peace and quiet, a place to focus without constant noise in the background, storage for books and papers, and a door to close for intense thought or private conversations. By now, I have spent enough time in open plan work areas to know that, for me at least, they are utterly destructive for concentration. The Bell Labs mixture of one's own private office and a shared place for the community worked well, very well. The labs. The labs also made it easy for people to keep on working at home in the evening. For many years, I had a dedicated phone line. After all, AT&T was the phone company in my home let me contact that let me connect to the UNIX system at Murray Hill so I could work evenings and weekends as phone line was connected to it. Okay, as an unexpected fringe benefit, there was a special access code that allowed us to make unlimited and unbilled long distance phone calls to anywhere in the US, which was rather a nice perk at a time when long distance calls cost actual money. Ken Thompson told me once on how this came to be. Joe Sana decided that we deserved home phone lines and teletypes. He invented a form to order them and made copies that he put in the stationery storeroom. He put himself down as the approver and then submitted several for the core Unix crowd. After several questioning telephone calls, Joe started getting the forms all filled out, which he approved. It was that simple. He just invented the form and it happened. In 1985, Peter Weinberg was promoted to department head in 1127, and a professional photograph was taken for the company newspaper, the Bell Labs News, familiarly known as the Bell Labs Good News, since it only printed positive stories. In a series of tactical errors, Peter left the original print of his headshot in the Unix room. What? Uh, okay, and a professional photograph was taken for the company newspaper, the Bell Labs News, familiarly known as the Bell Labs Good News, since it only printed positive stories. In serious tactical error, Peter left the original print of his headshot, figure 3.3, in the Unix room. Soon, this his image was all over the place, sometimes filtered through the AT&T logo, which had recently been introduced as Gerard Hausman says. Within a few weeks after AT&T had renewed the new corporation logo, Tom Duff had made a Peter logo, figure 3.5, that has since become a symbol for our center. Rob Pike had t-shirts made. Ken Thompson ordered coffee mugs with Peter logo. Where is the Peter logo? That is crazy. That is literally crazy. Over the years, Peter's visage showed up in dozens of places and organizations charred with Peter faces all the way to the top. A large array of circular magnets on his stairway was impressed in new laid concrete floors on microprocessor chips and most prominently in the night of September 16, 1985 on one of Bell Labs water towers. Figure 3.6. Peter Lowe. Fucking hell, that is just crazy. Rumors have circulated about who the painters were, but lips are still sealed more than 3 decades later. A reimbursement request for the paint was submitted, but it was rejected in any case. Within a couple of days, the water tower image was painted over by an official Dom that apparently did not share our sense of humor. The full story of Peter's many faces can be found at spinroot.com pwj. Nope. Website maintained by Gerard, who, with Rob Pike, did many of the original enhancements of Peter's picture. The labs was an informal place sometimes in the In the early to mid 1980s, a new policy was instituted. Employees had to wear their badges at all times. This was undoubtedly a sensible precaution to discourage interlopers, but it wasn't popular. As a protest, one colleague, who will remain nameless here, stuck his badge to his forehead with super glue. Another took to wearing it clipped to the hair on his chest, revealing it upon demand. And the badges had no security features. They consisted only of a picture in a template. Accordingly, we undertook a campaign to create a fake person, Grace R. Emlyn, who had her own login, GRE, her own badge, and from time to time an appearance on official lists and publications. Figure 3.7, GRE. That is crazy. They were having fucking fun there. I made my own badge with a Mickey Mouse image. 3.8. I wore it regularly, including one day at Bell Labs in Holmdel, New Jersey, for meeting with Bill Gates, who was there for some marketing for Windows 3.0. No one noticed. Figure 3.9 and 3.10 show random parts of the Unix office in 2005. Where this is Brian Kernighan's badge. He took it when he was going to meet Bill Gates. That is crazy. This is a part of Unix room, and this too is a part of Unix room with a bunch of books and Plan 9 from outer space and Buzz Lightyear and stuff. That is crazy. The Unix Programmer's Manual. One of the early contributions of Unix was its online manual in a now familiar format and concise style. Every command, library function, file format, and so on had a page in the manual that described briefly what it was and how to use it. For example, Figure 9.11 shows the first edition manual for page for the cat command, which concatenates zero or more files onto the standard output stream. By default, the user's terminal. Early man pages tended to be literally only a single page. Seamless, slimeness that is untouchable today. Early man pages tended to be literally only a single page. Slimeness that is uncommon today. Besides brevity, a couple of features of man pages were novel at the time, like the bugs section, which acknowledged that programs do have bugs or perhaps features imperfections that should at least be recorded, even if not fixed right away. The cat command hasn't been changed in 50 years, aside from acquiring a few options and probably unnecessary arguments that somewhat modify its behavior. It is still part of the core set of Unix commands. You can see its current status by typing the command is mancat. Yep. Yo, mancat. Concatenate and print files. Can I see who? Oh, there is the bug section. Because of the shell language mechanism used to perform output redirection, the command file this will cause the original data in file 1 to be destroyed. The cat utility does not recognize multi-byte characters with this and this in effect. Okay, I have, let's say, a couple of files. Wait, echo hi, how are, and that's it. Save it into file1.txt. Now echo space u. Save it into file2.txt. Now cat file1.txt and file2.txt and save into 1.txt. Cat file1.txt. It only got you. So let me store how are you back into file1 and do file 1.txt comma file 2.txt and append to file 1.txt. Let's see. It got stuck. Okay. That is crazy. There is a bug in the cat command. Man. In terminal windows on Linux, Mac OS, or Windows subsystem for Linux, and of course you can view the manual pages for the man command itself. Man. Okay. A few words about memory. I really want to write a program. Let me write my own cat command that would concatenate two files. Well, I have written my own cat command. It is called cat me, and it takes in a file one and prints it. What does it do? Shit, cat. Shit, that can file one. Oh, there is quite a bit of stuff in here. 500 lines of code. Okay, cat me file2.txt. How does that work? Wait, did I wrote that program? I wrote it in lang cls. Where is the function text.c? I guess maybe it was text.c. Nope. Echo.c. Nope. Oh, okay. So I guess it was cat.me and then something. Hello world. No. Print bell. Scope.c text stack rangefinder input redirection memory leak command line args command line argument.c only enter your name you dumbass. Take the name. Okay, that is fine. A few words about memory. Youngster readers might wonder about the accuracy of some of the memory sizes that I have been quoting along the way. Yep, for instance, IBM 7090 or 7094 had 32K, 32768, 36-bit words. The original ADP7 that can used had 8K, 8192 18-bit words, that is around 1/8 of the 7090 memory, and the first PDP-11 had 24K bytes of primary memory and a half megabyte disk. For comparison, my 2015 MacBook Air has 8 GB of memory, over 330,000 times as much, a 500 GB disk, half a million times as much, and they cost barely $1,000. In short, in short, memories were tiny, but by today's standards, where gigabytes of primary memory and terabytes of disk storage are cheap, compact, and therefore common, but memory technology in the 1960s and early 1970s was different. The primary memory of a computer was built from arrays of tiny donut-shaped ferrite cores connected with an intricate through though orderly set of wires that were threaded by hand through the cores. Each core could be magnetized one way or the other, think clockwise or counterclockwise, and thus was capable of remembering one bit of information. 8 cores could be a byte. Core memory was very expensive since manufacturing it took highly skilled manual labor. It was bulky and it weighed a lot. Figure 3.12 shows a core memory with 16 kilobits, 2 kilobytes, which in 1971 would have cost about 16,000 or dollar, close to a dollar a bit today, which is just crazy. This is the man page for the cat command. This is a magnetic core that is absolutely fucking crazy. People had to hand thread these things, and those are pins on the edges. Fucking hell. Okay. Memory was often the most costly component of a computer. When every byte was precious, that scarcity scarcity imposed a certain discipline on programmers who always had to be conscious of how much memory they were using and sometimes had to resort to trickery and risky programming techniques to fit their programs into the available memory. One thing that Unix did well was to make effective use of the limited memory of computers that it ran on. Some of this was due to exceptionally talented programmers like Ken and Dennis, who knew how to save memory. Some was due to their genius in finding ways to achieve generally and uniformity that generality and uniformity that made it possible to accomplish more with less code. Sometimes this was achieved by clever programming, while in other cases it was a result of finding better algorithms. Some was due to the use of assembly language, which at the time did make better use of instructions, run faster, and memory use less space than could be achieved with compilers for high-level languages. It was only in the mid-1970s that new memory technology based on semiconductors and integrated circuits became widely available at a price where one could afford the moderate but measurable overhead of high-level languages like C. Storage allocators like the original alloc and Doug McElroy's later malloc library were used to allocate and deallocate memory dynamically as a program was running out. Another way to make the most of a sacred resource. Naturally, this had to be done carefully since the slightest mistake could cause a program to work incorrectly, something that is not unheard of even today. I might add, at least as I observe students in my classes. Mismanagement of memory remains one of the leading causes of errors in C programs. When a program failed hardly enough, the operating system would notice and would try to help the programmer by producing a file of contents of main memory. Was the magnetic magnetic cores from which comes the phase core dump. When a memory failed badly enough, the operating system would notice and would try to help the programmer by producing a file of contents of main memory, what was in the magnetic cores, from which comes the phrase core dumped, still used through though magnetic cores long ago left the scene. The file is still called core. Okay, biography Dennis Ritchie. Now, what does core dumped means? Core dumped means that a program has crashed terminated unexpectedly and has generated a core dump, a snapshot of its memory of the crash. The dump file helps developers debug the issue by analyzing what went wrong. And yep, I have dinosaurs and stuff. It does not say that frames have dropped. That is crazy. And how does it happen? Segmentation fault, illegal instruction, bus error, floating point. Okay, something like this. I make a null pointer, then make it point to an integer. Dereferencing a null causes segmentation fault. Oh, segmentation fault core dumped. I actually wanted to do something like read. Okay, I will be starting after this, after when I have read, completed reading the Unix operating system, history and a memoir. I will start this course on stream. And I think this would be good because this has exercises and stuff. In every chapter there is extra exercise at the end of the chapter. See, this cool man has made all of these courses. Learn functional programming, and I will be reading about Git, about Docker, about C, Python, and Go mainly. Learn Go for developers. Well, I have not read Go, so that would be cool. Learning about the Go language. Complete the course and projects in order from top to bottom. Okay, I guess frames have dropped. Nope, frames have not dropped. That is cool. You are a guest to become a member. That takes money. You don't have money. Learn JavaScript for developers. Learn algorithms. I'm learning about algorithms. Learn to code. Learn Linux. Learn Git. Object-oriented programming. Build asteroids. That is going to be fun. That is actually going to be fun. Backend developer career path. 24 courses, 9 projects, 50 plus videos. 12 months. This is going to take me 12 months. Is it actually going to take me 12 months? If I do, let's say there are courses, how many? There are about 23 main courses, and then 1, 2, 3, 4, 5, 6, 7. 7 about 30 in total. And if I were to do just one course a week, 30 weeks, that is not 12 months. That is if I were to do one course a week, which I guess I can do. I will be streaming about 2.5 hours at least per day doing this course. Yeah, I guess I got this. And there's quite a lot of shit to do. Actually, quite a lot of stuff to do. Yes. So, yeah. Okay. Now I'm getting back to this, and after I have done this, I will start that and in the C language streams after I have done assembly code. Not assembly. After I have done advent of code, I will start doing. After advent of code, I will start building a web server in C from scratch, a chatting app server in which people can join and leave. And I will make the front end in terminal based so that people can talk to each other from terminal, like write the name of the program, then say rooms or join or something, and they will see it. This summary of Dennis Ritchie's life is adapted from a memorial that I wrote for the National Academy of Engineering in 2012. Dennis Ritchie, figure 3.13. Yo, here. He was born in September 1941. His father, Alistair Ritchie, worked For many years at Bell Labs in Moray Dennis went to Harvard when he did his undergrad work in physics and his graduate work in applied mathematics. His PhD thesis topic in 1968 was sub-recursive hierarchies of functions, and is tough going if one is not an expert, which I certainly am not. Figure 3.14 shows part of one random page taken from a blurry copy of a draft explaining his career path. He said, this is one of the pages from his thesis. Lemma is proven, concluding case 4. Okay, this is what he wrote. That is just so cryptic and makes me feel like I should learn about this. With time, with time, one thing at a time. But even if m equals this, and then t this, when you have given xk as function, the in negative, the inverse of x, you get 2, which is less than this thing. That is just crazy. My undergraduate experience convinced me that I was not smart enough to be a physicist and that computers were quite neat. My graduate school experience convinced me I was not smart enough to be an expert in the theory of algorithms, and also that I liked procedural languages better than functional ones. As Björn Stroustrup, Björn Stroustrup, the creator of C++, once said, if Dennis had decided to spend that decade on esoteric math, Unix would have been stillborn. Esoteric maths. What does esoteric mean? Uh, Esoteric meaning intended for or likely to be understood or enjoyed by only a few people with a special knowledge of interest. Esoteric. That is a good thing then. Esoteric stuff. That is just what we live for, isn't it? Dennis had spent several summers at Bell Labs and joined permanently in 1967 as a member of technical staff in the computing research Computing Science Research Center. For the first few years, he worked on Multics. As noted earlier, Multics proved too ambitious, and as it became clear that it would not live up to its goals, Bell Labs withdrew in 1969, leaving Ken and Dennis and colleagues with experience in innovative operating systems design in an appreciation of implementation in high level languages, and a chance to over with much more modest goals. The result was the Unix operating system and the C programming language. The C programming language dates from early in the 1970s. It was based on Dennis's experience with high-level languages for Multics implementation, but much reduced in size because most computers of the time had limited capacity. There simply wasn't enough memory or processing power to support a complicated compiler for a complicated language. This enforced minimality matched Meckens and Dennis's preference for simple, uniform mechanism. C was a good match as well for real computer hardware. It was clear how to translate it into good code then that ran efficiently. C made it possible to write the entire operating system in a high-level language. By 1973, Unix had been converted from its original assembly language form into C. This made it much easier to maintain and modify the system. It also enabled another giant step, moving the operating system from its original PDP-11 computer to other computers with different architectures. Because most of the system code was written in C, porting the system required not much more than porting the C compiler. Dennis was a superb technical writer with a spare, elegant style, deft turns of phrase, and often with flashes of dry wit that accurately reflected his personality. He and I wrote the C programming language together. It was published in 1978 with a second edition in 1988 and has since been translated into more than 24 languages. Dennis's original C reference manual form the basis of the ANSI ISO standard for C that was first produced in 1988 and was a major part of the book. Without doubt, some of the success of C and Unix can be attributed to Dennis's writing. With Ken Thompson, Dennis Ritchie with received many honors and awards for his work on C and Unix, including ACM Turing Award in 1983, the National Medal of Technology 1999, Japan Prize for Information and Communications 2011, and National Inventors of Hall of Fame posthumously in 2019. Hmm. What is posthumously? Wait, what? Ken Thompson, born in 1943. Dennis Ritchie, born in 1941. And okay, I will just uh, move on reading the next paragraph. Dennis was successfully avoided. Dennis successfully avoided a management role for many years, but finally yielded and became head of the software system department, where he was responsible for the group that was building the Plan 9 operating system. Dennis stepped down from management and retired officially in 2007, but continued to come to Bell Labs almost every day until his death in October 2011. Dennis was more modest and generous, always giving credit to others while downplaying his own contributions. A typical example is found in the acknowledgement section in his section of his 1996 retrospective of the evolution of Unix. The reader will not, on average, go far wrong if he reads each occurrences of V with a unclear attendance as Thompson with some assistance of me. Dennis died in October 2011. This note from his sister and brothers can be found on his homepage, yeah, which has been preserved at Bell Labs. As Dennis's siblings, Lynn and John and Bill Ritchie, on behalf of the entire Ritchie family, we wanted to convey to all of you how deeply moved, astonished, and appreciative we are of all the living attributes to Dennis that we have been reading. We can confirm the what we keep hearing again and again. Dennis was an unfallingly kind, unfailingly kind, sweet, unamusing, and generous brother, and of course, a complete geek. He had a hilarious, dry sense of humor and a keen appreciation for his life's absurdities, though his worldview was entirely devoid of cynicism or mean-spiritedness. We are terribly sad to have lost him, but touched beyond words to realize what a make mark he made on the world and how well this gentle personality beyond his accomplishments seemed to be understood. Lynn, John, and Bill Ritchie. Fucking hell. That is going to be the end of the stream for today. Fucking hell. Oh, fuck, shit. Yeah, bye.